Now let's focus on the DHCP server. This is an important daemon in configuring or auto-configuring the clients on your network. With that said, we'll set up a section labeling it accordingly. And that's the Dynamic Host Configuration Protocol daemon. And this daemon should be very familiar to you if you've worked with PCs or Linksys routers, bridges, or any device that may provide automatic configuration for your clients. So it provides automatic configuration of clients, and the package that we'll be working with does so for IPv4 clients, auto configuration, whereas IPv6 clients can be automatically configured by the default gateway if it supports IPv6, as built into the IPv6 protocol is a means for automatically configuring the client with the appropriate prefix. So it automatically configures IPv4 clients, but what's entailed, what's provided to the clients by the server? Well, the following are provided, but are not limited to the list that we'll provide, which includes IPv4 address, subnet mask, optionally a default gateway, DNS servers, NTP or time servers, WINS or Windows Internet Name servers or Microsoft WINS servers, and other useful information. Now what it provides, it being DHCP automatic configuration to IPv4 clients, it does so on a lease cycle. So it leases the addresses and related information based on predefined values. For example, 1 day, 1 week, 1 month, etc. So when you set up a DHCP server, not only do you specify key pieces of information, including the IPv4 addresses to lease, subnet, default gateway, and ancillary items, you also determine how long the lease is to be held by the client. The client will make sure to check in with the server on a recurring basis to attempt to renew the lease. We should also note, as a third feature, that DHCP uses the UDP protocol, which means it's fast, and it does so without having an address, so it makes use of UDP as well as the layer 2 of the OSI model. So DHCP uses UDP protocol and layer 2 information to request / assign addresses. And there's a process, a formal process, which is one of its features and can be referenced by the acronym DORA. So DHCP process follows the acronym DORA. First there's a discovery, then there's an offer. Now by discovery we mean the client broadcasts on the local subnet for a DHCP server. So if we take a look at our graphic, we can briefly summarize what happens here. And here's a topology. So let's suppose when we boot up any one of these systems, such as the VMware instance located, which currently has an address of 199 as opposed to 185, although it's not like CBT serve 3. But when the system boots and attempts to get an address automatically, it broadcasts that DHCP request out on the local subnet, and it uses UDP to discover DHCP servers. We currently have one DHCP server. That's this box here, the Media 1 box that I'm hovering over. We're going to install DHCP on our local system, Red Hat Enterprise, and disable DHCP on the other system, and we'll be able to witness the DORA process. But a discovery is sent out by the client, let's say the VMware instance, or another system on our network, and a DHCP server has to return with an offer. So a DHCP server returns an offer, so it's returned by the server. Now the offer that's returned is an offer to service the client. If the client's happy, then a request is made. In other words, if the client agrees, which it usually does, you may have one or more DHCP servers. So the first server to return an offer to the DHCP client causes the DHCP client to make a request for an address, a formal request for an address. So, formal address requests by client, which causes the server to acknowledge that the address that was included in the offer is actually being requested. So in other words, the server responds to the discovery, here's an address, would you like it? The client then requests the address, and then there's an acceptance. And this is where the acknowledgement occurs. So this DORA, four-step process, discovery, offer, request, and acceptance, happens between DHCP clients and servers. And we'll see traces of this in the varlog messages file when a client boots up and attempts to get an address from a DHCP server. Now with that said, let's move to, as usual, our tasks area. And our first task will be to install the DHCP server. No need to install the DHCP client, as it's built in with the operating system, or into the operating system. So it's already there. If you don't specify an IP address statically, the client will expect to go through the DORA DHCP process in order to auto-configure itself, or to have itself configured. Now the package that we will install, let's look through the repository here, using Control F, is the DHCP-3 package, as opposed to DH client, which is the client package, or DHCP v6 or v6 client. So the DHCP v6 package that is, represents a DHCP server focusing on version 6 of IP, and ditto for DHCP v6 client. Again, DHCP is not required with IPv6, but is there in the event that you need it. So, we want to turn our local system into a DHCP server, and then reboot our remote system to see that it gets an address, or to ensure that it picks up an address. So locally, let's find a root shell, and this is a non-root shell, so we'll SU in. We'll RPM query all grep case insensitive DHCP, although it's all lowercase as most packages are. And if it doesn't come back, we'll install it. Now notice, it is already installed on this local system, as well as DHCP v6 client. So let's enumerate the contents of the package using RPM query list, and we can contrast the version on the local system to the remote system 3057, or remote system that's also 3057. So the packages are identical. No need to reinstall. So query list of DHCP returns the contents of the package, including the primary configuration file, which we'll copy into our notes. This is where the bulk of the action takes place, where we set up the subnets and the address ranges and so on and so forth. We'll just note that it would have been yum y install DHCP. But with that said, our next task will be to configure etc dhcp conf dhcpd.conf, and this is the primary config file. We'll have to configure it with key information such as the subnet range. So this is that file. But also, because the DHCP is a service, it has an entry in init.d. It also includes a relay program in the event that you have clients on subnets where the DHCP server does not exist. So let's look at our graphic to give you an example. For example, in the DMZ subnet, if we did not have a DHCP server, supposing the Cisco router did not pose as a DHCP server, we could have a Linux instance in the DHCP, in the DMZ zone that is running the DHCP relay program to relay requests into the main subnet where the DHCP server resides. And it handles the forwarding of those packets for the DHCP clients on a remote subnet. Because by default, routers do not forward DHCP requests. Cisco routers can be configured to forward DHCP requests, but in the event that you don't have the type of router which can forward those requests for you, you'll want to install the DHC relay program. It is included with DHCP. There's a sysconfig entry for DHCPD, which we could take a brief look at, which contains general startup information for which there are none, DHCP arguments. There's also a program, OM shell, which allows you to configure DHCPD while it's running. The primary binary itself for DHCP, the daemon that is, the primary binary for the relay program, and as usual, documentation. And we should also note that DHCP maintains a leases file. This is where it records its database of leases. It records those leases in this file beneath varlib DHCPD, and it's able to determine what it's leased out as a consequence. So let's just note that. Note DHCPD records leases in the following file, and it maintains the lease information, which includes the options that were set, the IP address delegated or assigned, as well as the lease information, lease duration information associated with the assignment. Now we should also note that by default, etcdhcpd.conf contains useless information other than a pointer to a sample configuration file. So this needs to be configured based on the sample file. Let's take a look at that. We'll navigate to etc and less dhcpd.conf, and notice it simply points us to user shared doc dhcp, the version number of course, dhcpd conf. So let's copy the path and use less to tab it out, dhcp-305 dhcpd.conf.sample. Here's a sample configuration file that's useful for our intents and purposes. So what we'll do is copy this to the local directory as dhcpd.conf. We'll then, after we've overwritten it of course, we'll then manage it or open it using the nano program. And once in, you'll see some sensible settings. Global settings are placed outside of subnet blocks, and for obvious reasons, or it should be obvious, anything that pertains to a subnet will be contained within subnet blocks. So subnet 192.168.0.0 could pertain, and once we renumber it to 75.0, will pertain to the internal 192.168.75 network, whereas settings outside of the subnet block pertains to all subnets. Indeed, one DHCP server can service an unlimited number of subnets, providing the server has connectivity or is the target of a relay. So if multiple subnets relay either via a router, as we've seen in this case, or DHCP relay is running on Windows or Linux or any other OS into your DHCP server, then your DHCP server will receive the request for the various subnets and will need subnet blocks to be able to assign an address range to the clients making requests. But again, there are many global settings, and again, no need to memorize them because there is documentation, oodles of documentation included with the system. And you can simply let's log off this remote system here to take a brief look. If we RPM query list DHCP, and that's query all lists, that's the wrong option, so we'll kill it. And looking at the man page, we see dhcpd.conf. So if you man dhcpd.conf, we'll see the various directives that are supported in the file. Again, global parameters are outside of subnet blocks. Subnet blocks are subnet-specific parameters, such as default gateways. Those are certainly subnet-specific for multi-subnet networks. And there are many other settings supported by DHCP, such as the ability to group and set reservations and so on and so forth. We'll be looking at setting up a subnet as well as setting reservations. So let's return to the shell where the dhcpd.conf file is and begin definition. So we've got some directives for DNS and client updates, and these pertain primarily to Windows systems looking to update themselves in DNS, as well as Linux systems that want to update themselves with DDNS servers, or servers that support dynamic DNS information, changing DNS information. So for example, some of your clients might be DHCP, and if their addresses change from time to time, then that information needs to be republished to the central DNS server, whether Windows, Linux, FreeBSD, Solaris, what have you. The protocol is a standard protocol for updating DNS information. So with that said, let's make a few changes. We'll ignore the DDNS update style interim and ignore client updates. Just consult the man dhcpd.conf for further information and change the subnet from 00 to 750. The net mask suffices. It matches what we're currently setting. The default gateway, that is set with the option routers directive and is actually 75.1, not 0.1. We're not using an IS, so for any item you're not using, comment it out using a hash mark. The domain name is linuxcbt.internal. This is to be set on all internal systems. DNS servers include 75.100 and any other box that may service DNS requests on our network or off the network, such as an ISP system. Now, one of those hosts is a 68 address and can be indicated using a comma after the first entry. So internal host, comma, external host located at 68.94.156.1 will populate the client with this DNS address. And if you have additional DNS servers, just indicate them using a comma delimiter. It's that simple. Option time set, this is for Eastern Standard Time. NTP servers, we do have at least one. So we'll set 75.100. We're currently running no WINS servers, so we'll leave this commented. And so far so good. The definition of this particular subnet is in order. We do need to set a range of addresses. Otherwise, the DHCP server will not know what to serve to the client, so we must set a range. However, the keyword dynamic boot P is not required, so we'll just comment this out and include a new range directive indicating the lower address, which will be assigned last, and the higher address. Now let's say we want the range to be 100 through 200, or let's say 150 through 200. So 75.150 on the low end through 192.168.75.200 on the high end. This will ensure that the 200 address is assigned first, and it will decrement down to 150. So 200, then 199, 198, 197, and so on. We've got a default lease time measured in seconds, 21,600, divided by 60, that'll tell you how many minutes, and a maximum lease time. In other words, the client cannot hold the address and the address information beyond 43,200 seconds. This is the reservation section, which we'll comment for now. We'll turn on momentarily. This is a way you can ensure that a client is always served a specific address. And with that, the configuration is over. It's a very simple configuration. If you do have additional device types, by all means, add them. But this is all that's required to get the server up and running. So with that said, let's set up the server so that it starts automatically when the system boots by saving the changes to the config file. And we know that in etc init.d, the service exists as Dhcpd, so with that said, we'll check config Dhcpd on, or optionally using the levels option, we can determine which levels the service should run in. So 3, set service up to start when system boots. 4, disable service on 192.168.75.100 box. 5, start service on local hosts. And it will be up and running version 3.x. Now, the version running on the remote system is also major version 3, so the configuration is close to the version that we're running on the local system. So check config ensures that Dhcpd is on. If we now check config list, we see that it's set up for 2 through 5. And if we connect to the remote system, the 100 box, let's find a free shell here to be able to connect to it. We'll Control-Shift-T to open a new one. Then SSH to 168.75.100. And since it's a SUSE box, we'll rc dhcpd stop. This will stop the instance. And then we'll be able to start our instance locally. Let's go ahead locally and find a root shell. We'll execute service dhcpd start. And on the remote system, it's simply rc dhcpd stop. And to set it up when the system boots is check config dhcpd on. This sets it up in 2, 3, 4, and 5. So let's return to the shell, start Dhcpd locally, and barring no configuration errors, it should start as expected. And again, in var lib dhcp version, or for D for version 4, we'll find a leases file. This leases file will contain any leases issued. And we'll take a look at the less, using the less command, dhcpd leases. And in here we'll find entries for leases. Now supposing we don't want to alter the current configuration on the network, we can set up a reservation. For example, for this remote system, this 199 box, let's execute ifconfig. And it's not in our path, so we'll sbin ifconfig. We see that it has an address of 199. So our next task is to set a reservation. Set up dhcp reservation, which is a common task. And this requires the MAC address. So it requires the MAC address of the client. And it also requires that we indicate which IP address is to be reserved for the remote system. Remote system's MAC address is the hardware address returned using ifconfig. Take this address and build a reservation. So let's return to the shell to the config file on the local system. And there is a commented reservation section, and the host is called Dhcpd serve 4. This is just a descriptive name. The host name that's associated with it can be defined independently between the host blocks, or in between the host block. We need to at least uncomment hardware Ethernet address as well as fixed address, and then paste in the address, ensuring that the line terminates with a semicolon. The fixed address needs to be set to an address that the server is authorized to lease, 192.168.75.199, and the next dash server is unimportant. So we have a reservation that DHCP will honor. Whenever this MAC address comes in with the DORA request, it will be assigned this fixed address. We may optionally pass in options that are defined within the subnet block between the host block, such as a host name option, using option space host dash name space and in between quotes the name of the host. That host will be assigned, or the name will be assigned to the server if DHCP is allowed to configure the host name. But again, the prerequisites include the hardware Ethernet address and the mapped fixed address. So it requires the MAC address, requires the fixed address, which is basically the IPv4 address to map to the MAC address or to the client. The rest are optional. So see, optional options are supported between host block. So that takes care of reservation. But whenever you make a change to, or changes to the primary config file, one, you need to save it. Two, you need to restart the DHCP server. So service DHCPD restart to effect changes. And once we've done that, if all goes well, barring no configuration errors, the DHCP server will be up, running, and listening for requests from a specific host, as well as for requests from other hosts on the wire. But in particular, it will listen for and map requests from the specific host with a MAC address indicated by the reservation. This is the reservation block. When it finds this MAC address in the query, it will assign this fixed address, and expect to see the messages in var log messages. You'll find the whole DORA process here. You can watch it using tail while you restart a remote system. So for example, let's watch tail var log messages. This will continue to run as entries are added. And in a separate window, if we SSH is root over to the remote system for which we've set up a reservation, and then restart its DHCP service, or its networking service, that is. So in etc initd, we've got a network service. We can indicate that we'd like to have this service restarted, so service network restart. This will kick us off and restart the interface, and what will happen is a DORA request will be made to the DHCP server. So let's pause here to take a quick look at this interface. Pausing the screen, we mean. Here's a request. Here's an acknowledgement. Request for 192.168.75.199. So we look at the whole correspondence, and for 1034, which is where it began, remove host declaration, or remove 192.168.75.199. And from the dynamic address pool, .199 has been assigned. Here's a request for 199 from a given MAC address on ETH0. Here's an acknowledgement, which is the acceptance stage, the last stage. And that's the full process. So we're able to look at the DORA process, and we'll relabel DORA the last step, acceptance / acknowledgement, or acknowledgement. Relabel it as acknowledgement / acceptance. That's where the acknowledgement occurs. And we see the changes in var log messages. Now, how do we know indeed that our DHCP server has leased the address to the client? Well, we can consult the leases file. And let's do so on the client. And we still have an SSH session. Let's navigate. We should also note that the client also maintains a DHCP client directory which contains a leases file. If we list the contents of DH client interface.lease or leases, we'll see what we're looking for. Let's scroll down and we'll see that the lease originally came from the .100 system with various settings related to time, but now the leases come from the .10 box. This is the DHCP server identifier. The address is fixed. Here's a subnet, offset, EST timing, default gateway, lease time, DHCP message type, domain name servers, NTP servers, domain name, when the address should be renewed by, or when it was renewed, we should say, as well as rebound and expires. So when we should rebind the address at 2049 tonight, and when it expires at 2134. So at 1753 today, we will attempt to renew, not have renewed, but we'll attempt to renew at 1753. We'll try to ensure that we have the address fully by 2049, and by 2134, if none of the recent entries have worked, then we would have lost the address. But here's the most recent entry, proving that we've gotten the address from the appropriate server. So our server's up and running, and we can tweak the entries as we see fit and just grow the dhcpd.conf file to suit our needs. Primarily, you're going to place directives beneath or between the subnet block, but you'll also place some of the directives outside of the subnet block, such as NTP servers. Usually NTP servers are shared by clients across subnets within your environment. So we've got DHCPD up and running. Again, no SE Linux implications. And importantly, check config. DHCPD tells us it'll start in the multi-user run level, so when the system reboots, it'll come up. It's disabled on a remote system. We've configured at least one DHCP reservation, and we now know how to set up a subnet block with some options for time as well as domain and other directives. So let's continue our study of Red Hat Enterprise Linux in subsequent sections.